Okay, in this video, let's look at the titration of a weak acid and a strong base. The net ionic equation is going to be the weak acid, right? It doesn't ionize, so we'll leave it together, plus the strong base, so that's OH minus. So that's going to make the anion, or the weak of the the conjugate base, and water. So let's look at the titration of acetic acid, a weak acid, with NaOH, a strong base. And let's look at it at a whole bunch of different points, as we did with the strong acid, strong base titration. So to start with, let's say no sodium hydroxide has been added. So all I have is a weak acid. So when I say, what do I have? A weak acid, I make an ice box, and I figure out the pH of the weak acid just as we've done all along. Okay, so this is start to look pretty familiar. Right, so the Ka, I'm going to go ahead and make that assumption, right, because our Ka is big enough, well, small enough. So X is going to come out to be 0.00134 molar H plus, which gives us a pH of 2.87. So I'm going to go ahead and we're going to run a titration curve as we did also. So I've added none, so we're right about here to start with. So now what happens after we've added 10 milliliters of NaOH? So I'm adding a strong something. So we're going to go to completion. My weak acid, my strong base, water, and acetate. And I need an ICF box because I've added something strong. Now my acetic acid was 0.1 molar, and I had 50 milliliters of it. So it's going to be 0.005 moles. Okay, so 0.005 moles. And our NaOH was 0.1 molar. So that times 10 milliliters, or 0.01 liters, is going to give us 0.0010 moles. Okay. Don't care about that. So you can see you're going to run out of the OH minus first. Minus 0.001, minus 0.001, plus 0.001. So we've got 0.004, none, 0.001. So I look at my final row and say, what do I have? Well, I have a weak acid and its conjugate base, so I have a buffer. So we just go ahead and plug in our Henderson-Hasselbalch equation. Okay, 1.8 times 10 to the minus 5 was our Ka. Acid over base, 0.004, 0.001, 7.2 times 10 to the minus 5 molar H plus. So our pH is minus the log of that, and I get 4.14. So when I've added 10 milliliters, I'm up here somewhere. Okay, so I have a second point for my graph. 10. Now I've added 25 milliliters of NaOH. Okay, so this isn't going to change, 0.005 of the acetic acid, but now this is going to be 0.0025, right? 0.1 molar times 0.025 liters. None, don't care. You can see you'll run out of this first. Okay, minus 0.0025 plus 0.0025. So 0.0025, 0.0025. So I look at my final row and say, what do I have? I have a weak acid and its conjugate weak base. So I have a buffer. Okay. So H plus, Ka, acid over base. So pH is going to be 4.74. So that's at 25 milliliters. So we're up here somewhere. Now I want you to note, this is what we call the half equivalence point. Okay? It's a really handy thing to know. You'll notice I've added half as much OH minus as I have acetic acid. I'm halfway to the equivalence point, which is 50 milliliters. At halfway, you'll note that the moles of the acid and the moles of the base are equal. So at the half equivalence point, H plus always equals Ka, or pH equals pKa. It's a really useful way of determining the Ka or the pKa of an acid if you don't know it. So that's going to come in handy at some point or other, I'm quite certain. All right, next, let's add 40 milliliters of 0.1 molar NaOH. Okay, so we've still got 0.005, got 0.004, none, don't care. You can see you're going to use up this first. So we'll have 0.0010, 0, 0.0040. We still have a buffer. Okay, so nothing new and exciting has happened yet. Ka, acid over base, 001, 004. So your H plus is going to be 4.5 times 10 to the minus 6 molar, and your pH is going to be 5.35. So at 40 milliliters, we're up here somewhere. Okay, so we're sort of doing this right now, but we're about to hit the equivalence point in the next slide. So now 50 milliliters of NaOH is added. We're going to get a little more interesting. Okay, so 0.005, 0.005, 0, minus 0.005, minus 0.005, plus 0.005, 0, 0, 0.0050 moles. So we're at the equivalence point because we have no reactants left. I look at my final row and I say, what do I have? I have a weak base. Well, how do you find the pH of a weak base? Well, you write the equation for the weak base reacting with water. Okay, it's an equilibrium now because it's a weak base. So we're going to do an ice box. But what's the initial constant? Keep hitting that, sorry. So I've got moles, but I also need the total volume. So the total volume at this point is the 50 that I started with and the 50 that I added, so 100 milliliters. So 0.050 divided by 0.1 liter is going to give me 0.050 molar. Okay, so we've got 0.050 molar there. 0, 0. The rest of this should look pretty interestingly easy. 050 minus x, x, x. But I have a weak base, so I need the Kb. Well, Kb equals Kw over Ka. So your Kb is 5.6 times 10 to the minus 9. 10, sorry, 10. I can't add. Okay, so now Kb, 5.6 times 10 to the minus 10 is x squared, 0.050 minus x. Go ahead and make your assumption. Okay, x is going to come out to be 5.3 times 10 to the minus 6 molar OH minus. So now POH is 5.28 and pH is 8.72. So we're up here somewhere. So there were a bunch of places where you could mess up there, right? Once you find your moles, you got to find your total volume to get your molarity to plug that in here, because we need molarity, not moles. And then when you get your X, you got to recognize that it's OH minus, right? Not H plus. So first you find the POH, and then you find the pH. So that's kind of a lot more going on at the equivalence point. So I look at my final of this. Oh, God. All right, let's get past the equivalence point and see what happens. So I've added 60 milliliters of NaOH, so still 0.005, but now 0.006, 0. So we're going to use up this first. So that's gone. 0010. 0050. So I look at my final and I say, what do I have? I have a strong base and I have a weak base. When you have a strong base and a weak base, you can ignore the weak base. It's going to ionize so little that it's not going to matter. So all I'm going to do is look at the fact that I have a strong base. Okay? And the concentration of OH minus is going to be 0.0010 moles, but I need to divide by the total volume, so that was the 50 I started with, the 60 I added, so 110 milliliters, or 0.110 liters. So that's going to give me 9.1 times 10 to the minus 3 molar OH minus, so POH is 2.04, and pH is 11.96. So at 60 milliliters, we're at about 12. So we're here now. All right, one more point. Let's see where we are. 75 milliliters, so 0.0050, 0.00750. I'm going to use up this first. So there's none of that. 0.0025 of this. 0.005 of this. Again, I look at my final row and say, what do I have? I have a strong base, and I have a weak base, so I am going to ignore that. And the concentration of my OH minus is 0.0025 moles. Divided by, so the total volume is 50 I started with, the 75 I added, so 125 milliliters, or 0.125 liters. And we should have 0.020 molar OH minus. So POH is 1.7 and pH is 12.3. So at 75 milliliters or so, we're like about there. Okay, so this is going to look like that. So let's look at the overall titration of a weak acid and a strong base. Okay, so couple things to note. The pH at the equivalence point is going to be greater than 7, which makes sense, right? Weak acid, strong base, it makes sense it would end up being basic, right? The strong beats the weak. Note that we started at a relatively high pH, higher than we would have if it had been a strong acid. And also note that this rise here is much shorter than it was for the strong acid, strong base. It's a much smaller kind of rise. And that's it for weak acid, strong base.